All right. So this is going. This is going. All right. So this is going. Cool. We're good. Good. All right. Guys ready? Kevin, put your phone away. I am going to be that guy today. I haven't done that all year. You're distracting me. Divergence test, Kevin. What is it? Everyone's going to get called on today. I'm letting you know. Take your hood down. Thank you. We are in school. I am a teacher. You must show me respect. What is it? So if the limit does not approach zero, the limit of what? Nope, wrong. The elements of the sequence. So this is called a series. That is called a sequence. And when you add the terms of a sequence, it's called a series. I'm running in circles here. Diverges if so being a little informal / formal. All right, so we're moving on from that, but we'll continue to come back to it. All right, divergence test, harmonic series. Let's go to Anthony. What's the harmonic series? It's not like 1 over n. It is 1 over n. And okay, so I asked Kevin, what's the divergence test? Says this: the terms of the sequence, 1 over n is the sequence. This is a sub 1. This is a sub 2. This is a sub 3. They're the bib numbers of runners coming in. And when you add them, it's called a series. The terms of the sequence are approaching zero. But connection, it doesn't mean anything. I know I've said this too many times, but tighten it up today. It's Friday. It's a good day. And we're going to do a lot today. You're going to leave today being like, whoa, I make that promise to you. 1 hour from now, you'll be like, that was Mr. Hodge. You didn't lie at 9:15. That's why I'm recording this. I'm recording this right now, because you're going to want to come back to this. That is going to zero, but we've proved already. Matt said that he thought it was E, and I keep telling the story, not to pick on Matt, to build the story in your head so you have something to come back to and be like, no, that's the one. Like, it's not going to approach. That was the clever manipulation. This is a nice tool after talking about the divergence test. That just because it goes to zero doesn't mean it's going to make of some. This diverges. We'll come back to that later. However, a geometric series means we have a geometric sequence. So let's look at some of these terms. A plus sub n1, A sub r plus A sub r2, and so on and so on and so on. And it turns out this not only converges, equals not only will it converge, we can say what it converges to with that formula you need to know, only if the R value is in between -1 and 1. Another way of saying that its absolute value is in less than 1. And that's the picture of the square that's 1 by 1, and you add a half, and you add a half of that, and a half of that, and a half of that. Or someone asked, I think it might have been Anthony or somebody, like, does this work for thirds or 2/3? Think about that. Shade in 2/3 of the square, then 2/3 of what's left over. Yeah. And so 2/3 is an R value that's less than 1. Come back to that later. Integral test. Mentioned it. We're not there, but we're creeping towards there. In a free response potential question, if you're going to use the integral test, you must state before even using it that the hypothesis is met. And there are 3 conditions. 1, your function is continuous. 2, your function is above the x-axis. It's positive. 3, your function is decreasing. That's something you would have to kind of just make a case about. Rule of 3 is a way of showing something's continuous. Taking a derivative and showing that its derivative is greater than 0 is how we show something is less than 0 is how we show something is decreasing. And making an argument if something is positive, we'll see that when we need it. We don't have like an actual test, but just make a convincing argument. Then, so if this is met, then, and I didn't write this as clear as I should have last time. If the integral converges, the series converges. I know it's getting a little smaller. So, one thing to point out, 99% of the time is a fake statistic, but 99% of the time, this will be 1. Although, it doesn't have to be. At some point in time, the story goes like this. I might be like bouncing all over the place. I could be adding a lot, adding a little, doing something. But at some point in time, if my terms start going to 0, then I'm starting to diverge. It doesn't have to happen right at the beginning. And that's all that K value says. It doesn't have to be right from the beginning. But at some point, if you can find a function that converges, and that function is exactly the same as your series, even if it's not initially, but at some point it is, if your integral converges, the series converges. If the integral diverges, your series diverges. The big thing there I stressed a couple times is, obviously, if we're going to use this in the future, on an FRQ, for AP purposes, you must show those things. But in terms of mathematics and calculus, and when you go into your whatever science or math field you're going to study or not study, it's not that, you don't go through all these hypotheses. So knowing kind of both. For the AP reasons, we need to make sure we meet the hypothesis. But in general, for just the mathematics, for Calc 3 and beyond, these are, just important to make sure that your function that you're using is all those things and what the consequence, like what the outcome states. Want to know if this function converges or diverges. Before I write that. Is this function continuous? Yes. Why? Go ahead, Matt. Yep.
It is except that x equals -5.
Yep. So it's continuous except at x equals -5, where there's a vertical asymptote. 2. Is f of x greater than 0? What? So it's never greater than 0. This is never greater than 0. So the question is it greater than 0? Like Matt said, yes, except. So you're saying a hard no.
It is greater than 0 except when x is less than -5.
So your answer is yes if it's greater than -5, no if it's less than. We're trying to use the theorem, so we probably want to get to the yes. Is it decreasing? Calculus. I mean, I know the graph of this. I think you might know the graph of this. Side story, let's just side story. Like if this was multiple choice or just willy-nilly, 1 over x is what type of graph? 2 branches. And so you have a vertical asymptote, you have a horizontal asymptote, but basically this is going to shift it, as we're all recognizing, here. Right. Oops, that defeats my purpose there. But I know this is decreasing, right? Just because I know I've taken Algebra 2 and Pre-Cal, and I know this graph. So it is decreasing. That's my gut feeling. Secondly, it's above the x-axis because you have this asymptote. So we know we can use the integral test. We're just going through like the long process of, okay, AP writer, let me show you that I know my stuff. And so on the AP exam, as we're getting closer to it now, increasing and decreasing, I tell my AB students that is trigger words. That's a trigger word for derivative, first derivative. We can write this as negative x plus 5 to the -2, because I'm thinking this is to a -1 power. So bring down the exponent, subtract 1, take the derivative of the inside, you get 1. And This is -1 on top of x plus 5 quantity squared. I might even say to the test writer, this is always negative. This is always positive. And so therefore, this is going to be negative. Okay. I probably wouldn't say that to the test writer, but I would give this a little more flavor. I'd spend another 60 to 90 seconds saying, you know, like, this is a negative value, and I'd probably use a sentence or two. We'll come back to that. April's going to be about, like, formatting and everything back to life again. But we've essentially done it to some degree. All right? We've essentially shown yes, yes, yes. Therefore, I think I spelled that wrong. There is an E there. Okay. Why did that look weird for a minute? And then I'm like, no, now it looks even weirder. I'll let them correct me. We will take an improper integral of this. And I had you that's all. I didn't have you do any series work for homework. I just asked you to do improper integral review from another awesome YouTuber. I'm setting this up wrong. But we'd hit this with the limit as b goes to infinity. That's it. That's really it about improper integrals. They become limits. Whoop-de-doo. And you could use a U substitution. I think I can see it in my mind. If you can't, you could use a U substitution. What do you think it is? Yeah, so it's the natural log of the absolute value of x plus 5. Are we allowed to drop the absolute value? Yes, because we're starting at 1. And so therefore, it's really not a necessity, but it wouldn't be wrong to leave it on 2. But just making commentary at this point. So you could drop it if you wanted to, or leave it on. And now we're going to go from x equals 1 to x equals b. So we'd have the natural log of b plus 5 minus the natural log of 6. And that diverges. And in conclusion, if this was an FRQ, we state because the integral diverges, the series diverges, and you state the test. Even though it's like completely obvious all the work you've done so far, like, come on, what AP writer doesn't know? But you're going to get that last point, the 9 out of 9, by stating I find it tedious because I really don't want to take a baby derivative, but at the same point, I hope this is an FRQ because you should be able to slam it out of the park. It's just time consuming, maybe a little tedious, not even that exciting, but you're going to say continuous, decreasing, blah, da-da-da, boom, bing, boom, done. Make sure you state the test. All right. And that's kind of where we've been at so far. Are we kind of in agreement? Ready for some new stuff? No more new stuff. Well, too bad again, anyways. The remainder estimate for the integral test. All right, so we are officially creeping forward into something new. Just to kind of restate the objectives, because that was one of my objectives. One, just making sure where what we've been doing is continually brought back to life. So I'm going to ask again next week, what's the divergence test? What's this test? What's that test? We're like self-studying as a class by doing that. It's not to make us bored. It's like that's what, like, we're basically doing flashcards out loud. Say what it is, repeat it, repeat it, repeat it. That's intentional, right? But now we're officially moving into something new. So the remaining, no pun intended there, remaining part of today, we're going to look at this remainder estimate. I'm going to show you proof of it because it's cool and it builds to something else later. We're going to talk about a P-series test. So we're going to have it. This kind of ends the integral test. Close the door, open a new one. We're going to add a new test called the P-series test. Close that door, open a new one. We're going to talk about a direct comparison test and a limit comparison test. Dominance comes back into play, plays a major role there. And we're going to talk about like this converging, this diverges. You'll see what I mean there. As I said, pretty busy day, and next Wednesday and Friday will be equally as busy, and then we're done. Well, we're done with the series test. Then we get into Taylor polynomials, Maclaurin series, and then we are done with the curriculum right around the end of the month. So hang tight. We're really winding down. We got about 2-ish weeks, 4 to 5 more lessons of BC stuff. But I've built us up to this. It's not hard. We just need to lock in. Here we go. Suppose first I have to define what the remainder is. I'm going to add something in here. This is called an infinite series. This is the first term of that sequence. I know, redundant. That's the second term. This is the kth term. So this is just somewhere in the future. And it's going on forever. Hence the word adding an infinite sum of terms. Based on this, does this infinite series converge or diverge? Converges. I'm saying it converges. It equals something. We don't know what it is. That's okay. But because I'm saying it equals S, it converges. Cool. That's just making sure you understand vocab. Okay, next. The remainder So I'm defining what the remainder is. There it is. That's the remainder terms. What do we call this? It's a word we've used a few times. When you add and then you stop, this is called a blank sum, partial sum. So this is the partial sum. And so remainder is the remaining sum. That's, okay, makes sense now. Partial sum. And I wish they'd just use the word remainder sum, but they don't. They just say it's the remainder. What's up, Matt?
Is the term all the way to the right supposed to be a like of k plus 1?
Oh, yeah, my bad. Thank you. Yeah, that wouldn't make sense, right? So we know what the remainder is? It's like, okay, you have this infinite series. You chop it at some point. Well, now you have a partial sum because that's no longer infinite. It's what you didn't include, the remainder. Beating this to death, but now it's just coming to just like really quick. So using that geometric, that's a half, that's a fourth. Cool. And then the remainder would be this. Right. So we have a partial sum. That would be the remainder. All right, overkill. We use S sub k for the partial sum. We'll say R sub k stands for the remainder. And so if you take the partial sum and the remainder, you get the total sum. And therefore, the remainder is equal to the total sum minus the partial sum. Okay, this makes sense to me. That's cool, though. What's up? Mm-hmm.
Get new ones. Mine were stolen last semester.
And we're going to prove that. Oh, I wish we were back in our geometry 2 column proofs. If the infinite series a sub n converges by the integral test, then the remainder is greater than or equal to that integral, less than or equal to that integral. Oh boy, we're going to prove that. And then we'll apply it. What is that even saying? Let's go back to here. By the way, what is this a series of? What is this one? Starting at 0. You got it. So here's our partial sum, which our partial sum is 4, 6, 3/4. There we go. Is that truly what this sum is? No, we know we know the sum is 1, but pretend we didn't, right? But what I'm claiming is, all right, how far off are we then? How far? All this stuff, how far off is that remainder? How far off are we from the true sum? And this is saying the remainder is in between these two values. That's how far off you are from the true sum. We're basically going to say it's not 3/4, but we're going to be able to tell you how far at most we're off from a sum. Welcome.
Hi. Is this Mr. Simpson's room?
That one is. Yep. All right. So that's basically what it's saying a little cleaner. We'll apply in just a minute, but it's worth looking at why this is true. We use the integral test. What kind of function do we have? We have a decreasing positive continuous function. That's what it's called. By the integral test, how much are you off by? Reminding us something else we previously talked about. Series sequences use integers, so they're literally like discrete points. A function helps, but a function is defined typically for all real numbers. All right. And so what I want to look at is some left and right Riemann sums. How much area is that? I drew that a tiny bit off, but that's okay. Okay. What's going to bug me? Oh, that's not what I wanted. That's even worse. How much area is that rectangle? what did you say? A sub k minus 1? Y square root. Y squared. Yeah. Oh, square units. Okay, my bad. I was like squared. Okay, that's gonna. Yeah, so square units, cool. Yeah, we looked at this. That's why I said last time, guys, come up to board, and this is gonna be like similarly. This is what our sequence or series of terms is. It's these rectangular areas. Why did I stop doing that? Is it greater or less than the integral? Greater. It's over. Because you have a decreasing function when you take a right endpoint. I'm sorry. When you have a decreasing function and you take a left endpoint, as we're looking at, your Riemann sum is an overestimate. So that's definitely true. Now I'm going to take right Riemann sums. And so on and so on and so on, right? So there's a little bit of stuff there. And actually, I don't want this one. Actually, why not? I can fix what I want here. I was doing so well too. But this is fine. I'm going to fix what I wanted. What's true about that angle? If we look at right Riemann sums, it's going to be less than the integral Man, I wish I drew this picture correctly, but that's all right. I did draw it correctly. I messed up one thing. It's all good. How can I get out of this? I'm going to do it this way. Just hang tight. If you're copying, just pause for 1 minute. Let me clean up what I want here. I want, actually none of that. Same idea, but I just want to start right here. This is an overestimate, true? overestimate all the way down. All those rectangles are going to be an overestimate from the same integral from that point to that point. Now, if I look at right Riemann sums, and so on and so on, and so on and so on, and everything in between there. This is what I need to emphasize. How much area is this? Well, it's that height, right? So this is a Riemann sum of area like A sub k plus 1 units squared. Everyone agree? It's not like because we're using the left endpoint, we're using the right. All the way up to this one at the end, M. And that is going to be less than or equal to what integral? This will show me if you're paying attention and follow along. A sub k, right? So that's the kth input. That Riemann sum has this value, but the area starts from here to M. So we're starting at A sub k. That's really the essence of this proof here. It's all going to come together now. So on the right side, we have the same set of terms, same finite series there. They both start at A sub k plus 1. They both end at A sub n. And we have it trapped between two things. As m goes to infinity, the remainder is trapped between those two values. This would be the true sum. Infinitely. Obviously, we're not doing that. No one's doing that. We're going to find a partial sum of the first 5 terms. There it is. That is not the true sum. Duh. So how much error at most is there? Are we off by 0.5? That's what we're going to answer. Is what's left over 0.5, 0.6, 0.8, 3.2? How much are we off how much are we off by the true sum if we only take the first 5 terms? We just went through a proof. R sub 5 is less than or equal to the integral of 5 to infinity which is the limit as b goes to infinity Actually, I'm overkilling my minus signs. Let me clean this up. So it's going to be 1 over b minus, I double negative that. I'll do it this way. By choosing the first 5 terms, you are no more than 0.2 off from the true sum. Whatever that true sum is, you're no more than 0.2 off from it. You now can say, I don't know how to add an infinite series, so I'm going to take a few, and I'll tell you how much off it is from the actual total. And in an engineering field, I can see why this might be important. We want to make sure we're not risking anyone's lives or stuff like that. So we need very low error. 0.2, I don't know if that's low in science world. I would think that's a lot of error. So here's a more meaningful question. Find how many terms would ensure that the error is less than 0.01. All right, problem solvers, take over. You can do it. It's a new question. It's not a new theorem. This is it. We're going to move on to 2 more theorems after this. Use what we proved. Use the integral test. Use each other. Find the number of terms. Give you 5 minutes to get back on track here. What do you got, Anthony? You all done? Doing it in your head? Or are you done? What'd you get? How many? 101. Yep. What we don't know. We don't know this K value, but we want it to be less than or equal to 0.01. And that number comes from the integral of K to infinity of this function. So basically, focus right here. We need to solve this for K. 0.01 equals the limit as b goes to infinity of K to b of x to the negative 2 dx, blah, blah, blah. We've just cranked through this. So eventually you get to up. Well, let's just do it. So limit as b goes to infinity of negative I think we'd end up with that, which is 1 over k. Let's see, so we do the power rule like we did before. We would then evaluate it at b minus k, and you'd end up with that expression. And then as b goes to infinity, you're left with 1 over k. So we have 0.01 equals 1 over k, which means k equals 100. So why do we need 101? Yeah. So to guarantee it's definitely less than, you want to take 101 terms. So maybe that was a trick, but it's also an opportunity. So that inequality says it could be less than or equal to. So maybe at 100 terms, it is equal to 0.01. We don't know. The fact that it has to be strictly less than, you want to take the next term for sure. Yeah. All right. So if you were thinking 100 or you got to 100, cool. But that's what we call like the error in the integral test. And the reason I went through that proof, although I messed it up, is when we get to a more intense error bound, because we have an alternating series error and then a Lagrange error, having a visual will help. All right. I'll try not to mess it up next time. All right. Almost on track to where I want to be. Told you it was going to be a big day. It's almost been an hour since I said that. P series. Think you did part of this as part of your homework? Maybe not. No. Did you? Yeah. All right. That's what I couldn't remember if that was part of it or not. If you see a series whose sequence of terms does not go to 0, diverges by the divergence test. All those things we said before. If you see a geometric series and the R value is in between -1 and 1, not only does it converge, there's a formula for it. That's how I started today's class. We have the integral test. If you see a series and you're not sure, I don't know, it's not geometric, but I do know it's going to 0, it's not harmonic, but it's decreasing, it's positive, I can take its integral, boom, you hit it with the integral test. And furthermore, you can find out how much error. You might not be able to say, if it does converge, you could say, what we just did there, all right, if you grab this many terms, the error is less than or equal to this. Or if I need to know how much or how many terms I want so that I'm within some error, you just kind of work backwards. You'll have some practice, obviously, for homework. Sorry, but it is what it is. So now close those doors and open a new one. When we see a series, if we see a series that doesn't meet any of those criteria, however, we recognize it as 1 over n to the p, you can, on the AP test, just tell the reader or in your mind, that's a P series. And if P is greater than 1, it converges. If it's less than or equal to 1, it diverges. And that's it. You wouldn't have to say any more. You say by the P series, it converges, nothing else. I'm going to take a moment here and try to put some stuff together. If P is 1, what do we have? Thank you. If P is 1/2, I'm going to go somewhere with this. Then we'd have 1 over n to the 1/2, which is n to the -1/2. What I'm trying to do right now is giving you a study tool and make a big connection. Maybe it won't be made. Made a connection for me. What graph is this that I just kind of dotted there? Square root. That would be n to the positive 1/2. What's n to the negative 1/2 then? It's reciprocal. So this small output right here would reciprocate really large. Now, square roots are increasing, but slowly. Like to get to 10, you have to go all the way out to the number 100. Keep that in mind where I'm going with this. But eventually, it will reach 100 or 1,000,000. So eventually, it does become small. But that's where I'm going with this. It was my Harvard professor who explained it this way. This curve is positive, is decreasing, is continuous. The terms are going to 0, but they're not going fast enough. Because a square root does increase, but slowly. When we reciprocate, that big output does eventually become small, but just too slowly. Let's go back for the harmonic one. N to the negative 1. Well, here's n to the first, which is a linear function. This small output reciprocates to big. Okay. This gets to 100. 100. Let me rephrase that. This gets to 10. At 10, well, that's quicker than the square root. See where I'm going? Like, does this output 10? Yeah, you have to go out 100 terms. So it's reciprocal. Wait, it's not decreasing fast enough. This outputs 10. You only have to go out to 10, not to 100. But it turns out that still was not fast enough. That one will diverge as well. We've already proved it. Boom. Now, if n was 2, then that's n to the negative 2. I'll put this actually on the tablet, which is a square root, is a parabola. Hey, come on. And so this small output reciprocates to big. This big output reciprocates to small. Does it eventually output 10? Yeah, pretty quickly. 3 outputs 9, so a little more than 3. And that's how my Harvard professor described this to us. Notice all of those graphs all kind of have this type of behavior. But which ones kind of decrease fast enough? The ones beyond the harmonic. The harmonic's really the line, literally, that's no pun intended there, but it's the point that says, bro, I'm the divider between who's going to converge or diverge. And so I just wanted to share that with you because it's a different way of like thinking about it. All these tests feel, eventually, there's a few more to come, overwhelming, but I'm going to go back to this throughout this course and say, let's think about these graphs. Are they decreasing fast enough? And if we know some parent functions and we can build their reciprocals, I think we'll be able to answer a lot more questions than we did last year, although we did really well last year. While I'm on this whole case, what about 1 over 2 to the n? Well, that would be 2 to the negative n, known as 1/2 to the n. I guess I could have done that from the beginning. Known as exponential decay. Again, it has this same vibe as everything so far. We need to be decreasing, positive, continuous. All these graphs that we have so far seen converge have this behavior. So if you can relate it to graphs, you can get some insight about what will converge or diverge. All right, so the P-series just says, in general, that. If P is greater than 1, it's going to converge. I just explained why. Otherwise, it's going to diverge. Will this series of terms diverge or converge? That's what my brain instantly goes to. I'm not going to worry about that one. If you got another way around it, cool. I'm not going to worry about that initial one. Oh, yeah, what? 1/2 cube root of n.
Isn't it 1 over n cube root of n though? Because like yeah.
What am I missing?
Going 2, 3, 4 outside of the.
Yeah. Okay, I got you. Good. My bad. Okay. I was totally not it. I knew that, and I'm not even. Thank you. 1 over n cube root of n. My bad. So I saw that immediately. Now it turns out the 1 is going to play well here, but I saw that immediately, and I'm making a point here. Now I can work with this. That's 1/3. That's going to be 4/3. And so since P is greater than 1, this will converge. Now, if I forget that, because there's a lot of things on the test day, right, I might just say, all right, let me think about the graph of 1 over n to the 4/3. That's n to the negative 4/3. That is like a cube root that's being 4th power. So if you had a graphing calculator, you could think about it that way, or just kind of talk through it, but then say, oh, okay, that's that conversation where it's decreasing faster than a harmonic. So yes, it will work. Now, earlier today I said it doesn't matter what happens to a sequence of terms or a series of terms or something before a point. If at some point a series behaves in a certain manner, then what happened before, just think of it this way, we can add that all up. But at this point, if it converges, say this total is 100. If it converges, then it's 100 plus the convergence. But that's still going to